Hello everyone, and welcome to our final session on Summary of Big O Concepts. As I already mentioned in our earlier sessions, we've spent the last 14 sessions diving deep into algorithm analysis using Big O notation. Today, we're going to recap those essential ideas, review how performance scales with input size, and summarize the key concepts we've covered. Let's begin. Let's start with a brief introduction. As I mentioned in our previous sessions, Big O notation is crucial for understanding and predicting algorithm performance. To recap again, our agenda today includes: what is Big O notation? A review of common complexity classes. Discussion of best case, worst case, and average case scenarios. Visual demonstrations of algorithm behavior. A final summary and Q&A session. This overview encapsulates everything we've discussed over the past sessions. As I already covered in our earlier sessions, Big O notation is a mathematical way to describe the upper bound of an algorithm's runtime. It focuses on the worst-case scenario as the input size grows. To recap, it abstracts away constant factors and lower-order terms, enabling us to compare algorithm efficiency and understand scalability without getting lost in the details. Let me remind you of the key characteristics of Big O notation that we discussed before. Scalability. It expresses how running time or space requirements grow with input size. Upper bound. It provides a guarantee on the worst-case performance. Simplification. By ignoring lower-order terms and constant coefficients, it emphasizes the dominant factors affecting performance. Applicability. It's relevant for both time and space complexity analysis. These points have been a recurring theme throughout our sessions, so let's recap them once more. As we covered in our previous sessions, here are some common complexity classes. O(1) constant time, execution time remains constant regardless of input size. O(log(n) logarithmic time, growth is very slow, even as the input size increases. O(n) linear time, runtime scales directly with the number of elements. O(n log(n) linearithmic time, found in efficient sorting algorithms like merge sort. O(n squared) quadratic time, runtime increases with the square of the input size. Now, let's revisit the different performance scenarios we talked about before. Best case, the minimum possible running time, which can be as fast as O(1) or O(n). Worst case, the maximum running time under any input condition. This is what Big O mainly focuses on. Average case, the expected running time for typical inputs. As I mentioned earlier, these distinctions help bridge theoretical performance and practical application. The chart here is a recap of our earlier discussions on these scenarios. As I already explained in our previous sessions, expressing algorithm efficiency involves using mathematical models to describe performance as the input size grows. We focus on asymptotic behavior, what happens as n approaches infinity, using limits to simplify comparisons. This approach allows us to evaluate trade-offs between speed and resource consumption, which is essential when choosing algorithms and data structures. To summarize everything we've learned, Big O notation is a powerful abstraction that lets us understand how algorithms perform and scale. It emphasizes scalability and provides an upper bound on performance by focusing on the worst-case scenario. By abstracting performance details, it allows us to compare different complexity classes effectively. As I've stressed in our earlier sessions, the simplicity and power of asymptotic analysis are key takeaways for designing efficient algorithms. This recap should serve as a comprehensive summary of all the Big O concepts we've covered. Thank you for your attention throughout these sessions. I now invite any questions you may have about the topics we've revisited today. Feel free to ask about any practical applications of Big O concepts or any details you'd like to discuss further. You can send your question in the comment section. Before we conclude, I want to thank you for joining all 15 sessions on Big O notation. Starting in our next session, we'll shift our focus to arrays, building on the strong foundation we've established here. Big O concepts are vital for understanding data structures and algorithms, a focus for all major tech companies. If you missed any of the earlier sessions, please review them to get the full picture. On this note, I'm wrapping up today's recap. Thank you once again, and I look forward to our next session.